Hello, everybody. So this is section 3.4, motion in space. So we are primarily talking about things that fly, projectiles, for instance, or maybe baseballs in R2 and R3. All right, so we'll use our vector analysis to analyze these flying objects. So let's get started on section 3.4 in Calculus 3. Okay, so here is how things start. We are going to suppose that a function is given, vector valued function is given, and this is in three-dimensional space, xt, yt, zt, as before. Okay, so this is and we assume this is a position function. This is the position function. In other words, R of t is describing the position of an object, a projectile at time t. Okay, so it's the position function. And let's just write down, spell this out, function. Okay, and so if you take the derivative of this, what do you get? I think it's pretty obvious, right? You get the tangent or something that represents the direction and the speed of the motion, which is called the velocity function. No problem here, right? Okay, and then if you take the norm of that, the magnitude of it, okay, so this is the magnitude of the velocity function. What do we call that? It's like the absolute value, and it is the speed. Right? The speed is a real valued function, not a vector valued function. And then if you take the second derivative of the position function, which is r double prime, which is also v prime, because v itself is the derivative of the position function, that becomes, of course, the acceleration vector. And so this is called the acceleration, the second derivative. All right. Not too bad, right? It's not as difficult as some of the other stuff that we have studied. All right, now we have a typical kind of question called IVP, the initial value problems. Let me just write this down because you should be familiar with this term, the initial value problems. So what is that? Well, we are given some initial values, right? So we will be given the acceleration and then the initial velocity, which is v sub 0, right? And v of 0, but we also call this v sub 0. This will be denoted with v with a subscript 0. We call this v sub naught or v naught. And then we are also given the initial position, which is r of 0, which we abbreviate as r naught. Okay, so these are given. And basically, you understand what's happening, right? You'll be given the acceleration vector. And from there, we do the opposite of differentiation, which of course is the integration process, finding the antiderivative, and plug in v naught to find the velocity function. And then we do the antiderivative or integration again to get our position function, right? And you can see how this is such an important application when we study any sort of an object that's moving in space. All right, so let's do an example. So here's our example. Let's say the acceleration is given as 6 sine 2t, 2 cosine t, and 1. Okay, so what's going on here? And by the way, this is in meters per second. We call it meters per second squared, right? And this is how the acceleration is described. It's a rate of change of velocity per second. So it'll be meters per squared second. Okay, and then we are also going to be given some initial values. For this, you need 2 initial values to find our unique solution. And that's going to be v naught, which is given as -3, 1, 0. I am just, giving you the an example question. So, and then the position let's assume it's 0, 0, 4. Okay, and of course, our job is to find the velocity vector function and the position function, given these three pieces of information. Okay, all right, so how do you start? Well, of course, you start by integrating the acceleration function. So you have 6 sine 2t. What is the antiderivative of that? That would be negative 3 cosine 2t. And again, every time I do this, I make sure, as soon as I do this, I try to differentiate this so that I will be sure to get 6 sine 2t. And in this case, of course, it's negative 3 times 2 times negative of sine 2t, and that's going to be 6 sine 2t, so that's fine. All right, and then, so that's the velocity function, the first component of it. 2 cosine t, the antiderivative is negative 2 sine t. Oops, that's not true. 2 sine t, because it's positive, right? And then 1, of course, becomes t. All right, so that is the an antiderivative, but remember, you have a constant. And in fact, for each component, you have a constant. So I'm going to write that constant as a constant vector c1. Okay, so that's no problem, right? Now, what are we supposed to do? How do we find C1 in this? Well, that's not too hard. Okay, so what do we have to do? We plug in the initial velocity. The initial velocity is going to be, you just plug in. So yeah, basically, I should not be writing this. It's going to be V sub 0. Okay, so V naught is V, where t is 0, of course. So plug in 0, okay? So you have cosine of 0, which is 1, so that's negative 3. Sine of 0, of course, is 0. And t, when t is equal to 0, is, of course, 0. And so this plus c1 we are given is negative 3. Remember that? Negative 3, 1, and 0, okay? So that's what's given. And so I think from here, it's easy to figure out C1, the vector is, okay, what is that? It's 0, 1, 0, right? Basically, all you have to do is to take this and subtract, take this and subtract this from it, and you get 0, 1, 0. No problem here, right? Okay, so now we have a complete description of the velocity function. It is negative 3 cosine 2t, that's this part, plus 0, and then 2 sine t plus 1. Okay, now this is important. Okay, and then t plus 0 is, of course, t. So this is our complete description, or the full answer for the velocity function. Negative 3 cosine 2t, comma, 2 sine t plus 1, comma, t, right? It's important to denote that, right? And now we go backwards to the position function by integrating this again. Now this could be a little tricky. Negative cosine becomes negative sine. And so you, because of the chain rule, you'll have negative 3 halves sine 2t. Okay, again, immediately I try to differentiate this thing, and you'll see that it's going to be negative 3 times cosine of 2t, so that's fine. The antiderivative of 2 sine would be negative 2 cosine t. Now remember, this plus 1 was important because this will now become an actual variable t. Okay, now t becomes 1/2 t squared, right? And so that's our antiderivative. And of course, you have something else here, right? So it's going to be plus what? C2, we have a new variable right here. And that's what's going to be different about this. Very much like the first time, right? Now let's plug in our initial velocity, initial position, R naught, which is R at 0, because that's the initial position. And so when you plug in 0 for t, you get 0, negative 2, and 0, plus C2. And we are given, remember, we are given that R naught is 0, 0, 4. So it's going to be 0, 0, 4. And that is going to give us C2. What is our C2? Well, C2 is going to be this minus that, right? So it's going to be 0, positive 2, and positive 4. The arithmetic could be tricky, so be careful, right? Okay, so now we have our final answer here for the position function. Great, isn't it? Okay, what's RT? Well, that's basically what we have here, plus you plug in, 0 to 4 for your constants. So it's -3 halves sine 2t. It's plus 0. -2 cosine of t plus 2. Okay, and then 1/2 t squared plus 4. All right, so finally we have this as our solution to this initial value problem. Okay, any questions? I want to make sure something here, just checking. All right, no problem, right? Okay, so maybe what I can do is just to emphasize that this is the answer. This is our final answer. Okay, I'm going to maybe, can I change the color? I think I can. No, it didn't work. Okay, anyway, so this is our final answer. All right, now I would highly recommend that once you solve an initial value problem, check and make sure that if you take the derivative of this, okay, you actually get the velocity function. And the second derivative is the acceleration function. Okay, you can also check for the initial value as well. Right? Now, let's say, in addition to this, for some reason, somebody wants to know how fast this is going, the speed, which is a numerical value, not a vector, a scalar. I mean, it is a scalar, not a vector. Find the speed at t is equal to pi, okay, second. So pi seconds later, how fast is this object moving? Okay, now what you can do is you can try to, I wouldn't do it, but if you are so led, you could try to do this velocity, try to find the magnitude of the velocity function, which is what, square root of, and remember you have this velocity function right here. Okay, so this will be 9 cosine square 2t plus the second part is 2 sine t plus 1. You have to square that quantity, and then plus t square. All right, and then you can evaluate this at t is equal to pi. All right, now you could do this. It's a mess, right? I mean, because you have to open this up and try to multiply this out. Okay, well, so I wouldn't recommend this. If you are given a specific point, right, or t is equal to pi, just try to find out v of pi. What is the velocity at t is equal to pi? Now, remember, you have this equation for the velocity, right? So just plug in, plug in a pi for, this disappeared, pi for t, and what happens here? Well, the cosine of 2 pi is going to be 1. So this will be -3. And then 2 times the sine of pi, that's 0, plus 1. And then t is, of course, pi, right? So that's a lot easier because it's very specific. And so you can figure out the velocity, or not the velocity, but the speed at t is equal to pi is the square root of 9 plus 1 plus pi. And that's the square root of 10 plus pi. And you can figure this out if you, it's pi square. Okay. And so it'll be about 4.457. And of course, units are meters per second. Okay, so that's that's a much easier way to find this. Okay, so having said that, we have a special application. I mean, this is an application of vector calculus already, but a special application is going to be a motion. And we'll describe this on the plane. okay, due to gravity. So when an object, and what I mean by gravity is that universal gravity on the Earth at sea level, technically. And so let me just mention this. I have a little picture that I have drawn earlier. And so this is what's happening here. And again, I think you have a question about how far a baseball is fly. Would it go over the fence or not over the fence? Assuming, oh, by the way, an important important thing here, without considering air resistance. Now, if you think about it, it's really stupid. Like, when in the world are you going to have a problem without air resistance, right? I mean, even on the baseball field, everybody knows that the winds actually change things quite a bit, significantly. And air resistance itself changes things significantly without even the wind. So how silly is it to consider problems without air resistance? And my answer is, well, if you can't do this problem without air resistance, there's no way you can consider air resistance. So learn this basic thing well, and then you can find real problems with winds and air resistance. Okay, so basically any projectile neglecting air resistance and winds are going to fly along a parabolic path, right? A second degree quadratic formula, quadratic equation, quadratic function. So here's the initial position. In this case, the initial position is x naught, y naught, and that's, of course, given here, right? And then you are given the initial velocity, But an object is subject to one force and only one force if you don't have of air resistance, and that is the acceleration due to gravity. That's in this XY coordinate system, it's 0, -32. Now, where did this number come from? Well, this is the number that has been, well established, and this is feet per second. So it's feet per second squared. And what this is telling you is, if you consider all the forces, basically one and only one force that's applied to this flying object or projectile is the gravity. And when you consider gravity, the first component, the x direction, is not affected by this, 0, no acceleration in the x direction. But the gravity, of course, forces things down, and that force is -32 feet per square second. Now, if you live anywhere besides the United States, of course, you use the metric system, and that constant is -9.8 meters per second square, right? And so that's what happens in this. Now, let's see, what I want to do is to maybe give you a problem here. And oh yeah, okay, I guess I should have mentioned something else too. So you're given this R naught, which is the initial position, x naught, y naught, okay? And then you are given the initial velocity, x1, y1. That is this blue arrow, the blue vector. And of course, that itself is the magnitude of the initial velocity times cosine of theta, because that's the x coordinate. And then the magnitude times the sine of theta, where theta is the angle of, the launch angle. That is our initial velocity. So what I want you to do is to use this information, whatever is given here, okay, and the fact that the acceleration is 0, -32, to find the velocity and the position function, just like we had before. And so try to do that. And when you think, well, I'm going to give you a pause for a moment. And when you think you get the answer here for the position function, okay, using things like x naught, y naught, and x1 and y1, then you can come back and look at part 2 of this video. And and I'll try to describe what this picture here means in part 2 as well. Okay, so go ahead and work on that. And when you think you got the answer, go to section, the part 2 of this section. All right.